Welcome back to what will be the second last bit of content, so just a little bit to go. So this time we're going to be looking at pedigrees, and through pedigrees we can start to look at inherited traits through more of a family tree. We're going to be looking at recessive and dominant traits again, but another way to represent those and looking at it being transferred on in a few more generations. So from this, after this, you should be able to construct and analyze pedigree charts. So we'll look at how they're constructed and the symbols that we use for them, and describe the role of genetic testing and decision making relating to embryo selection and identification of carriers for genetic mutations. And then the last video that we will do, not actually this one, will be a brief look at a process called gel electrophoresis, and we will actually do this in class as well. You'll actually run a gel in one of our next classes. So a pedigree is a diagram that shows the occurrence and appearance of phenotypes of a particular gene or organism. So previously we've seen Punnett squares, and we've looked at how those combinations, allele combinations, can end up giving us different proportions. Whereas a pedigree is like a family tree that shows how a trait is passed through, so affected or unaffected people for a particular trait. So we use particular symbols for these. So if someone has the trait, then the symbol that represents them is colored in. So we would call this shaded. So we could have two options as a shaded or unshaded. So someone who has a shaded symbol would be affected, okay, and then someone whose was unshaded would not be affected by that trait. They would not phenotypically be representing that trait. So in this case, or in all pedigree cases, because we're usually looking at males and females and the offspring that they have, a female, okay, will be represented by a circle, so that could be shaded or unshaded, and a male will be represented by a square. Again, this can be shaded or unshaded depending on if it is affected or unaffected. And then that we will follow their offspring through the trait. So if we use analysis, we can then follow which characteristic is dominant or recessive by looking at what combinations of children come from the breeding pair. So this is an example of some pedigree charts and a key to the pedigree. This key will always be used for all the pedigrees that we look at. So if it is colored in, it is affected by that trait. So phenotypically we would see it. It would be an observable trait. If it is unshaded, it will be not affected by the trait. So if we were to look at this pedigree here, we can see that in this case, this would be a female that would be affected by the trait. This is, because it's square, going to be a male who is unaffected. Okay, at this stage, we don't know if it's sex-linked, we don't know what it is. These are just the two possibilities. So we can see here that the children, we have a female child and a of this pairing, and they have married a male. So the male is not of these two here. Okay, so we can see here that the female is unaffected. Okay, and then they have married an unaffected male, and the children that they have, so the children are on the next tier down. There is a affected male, and there is an unaffected female child and an unaffected male child. So we know that in these two, there had to be a carrier. Okay, so there had to be a carrier. We know the trait must be recessive because it hasn't come across in this individual here. So if it was dominant, we would likely see it in this individual here. So we can use this to analyze different situations. So let's have a look. So this is a pedigree showing the inheritance of a genetic disease. We need to work out if the disease is recessive or dominant. So the first thing we want to do is check our key. We want to look at the key, and we can see that a light blue square is going to be a male, our peach circle is a female, and then the darker purple square is a male that shows that characteristic. We also have some combinations here for identical twins, non-identical twins, and then we can see here that with each level of the flowchart that we see, each level of the pedigree, it shows a different generation. So if we want to look at this and figure out if it's recessive or dominant, there's a couple of stages that we follow. We can see here that the parents are unaffected, but they have two offspring that have been affected. So if the parents aren't effective, it must be recessive. Okay, so the parents aren't showing the phenotype, but when they combine, the phenotype for the effective turns up. So if we think back to our dominant and recessive Punnett squares, we can see in this case that we would end up with a potential for an affected child if they were both heterozygous, if they were carriers for this trait. So we can, and that would be if it was a recessive trait. If it was a dominant trait, then we would see it turning up in the parents as well, but it only turns up in the offspring. So in this case, if we have a look at this pedigree chart here, we can see we have from our previous key, this is an affected male with an unaffected female. Okay, they have 3 children, an affected male and 2 unaffected females. And then we can see here that the male child from this pairing of an unaffected male and an unaffected female is actually affected. This would indicate that it's sex-linked because the female children don't show it. The male children do, and we can see clearly here that the female here must be a carrier because the male didn't show it here. So it would show that it was an X-linked disease because we don't see the female children having it. They can be carriers, but they're not tending to show the trait. So if we have a look at this, this is what we were talking about before in terms of our sex-linked, which we've already talked about. Okay, so because we have the affected male, we know that they are X and they have the trait it is being shown here. We know that on the female, we have these 2 options. So if we follow this through, then we know that this female must be in this combination as much this one as well, so that when the female and the male produce the male child, we have an affected trait. So this must be the pairing here. The recessive one is showing here. Same with this situation here. So the X is going to come from the mother and the Y from the male. So we must have this combination because when the dominant was present, it didn't come through. Which would mean that in this case, because this is an unaffected male, this female here can be a carrier. They're likely to have the same genotype as what we saw in our parent generation, our first generation here, where they would have this combination and be a carrier for the trait. So this one is looking at a widow's peak. It's a recessive trait, okay, and we can see, looking at the family tree, we can see here that this is a male child. Okay, the relationship between 12 and 13, remember our key before, these are identical twins and they are both male. Okay, going back to our key here, we can see that they were identical twin boys. So we have identical twin boys here. Okay, if we look at number 2 and number 11, okay, so 11 here, this is their father came from here, so this must be the grandmother. Okay, and grandson, because this is the male, so this is the father, and then this is the father's mother. Okay, 12 and 13 are identical twin boys, and then the genotype of 2. So we can see here that this is the affected, it's shaded in. So we know that if this is the case, then the genotype for this one, we'll use W is equal dominant, and little w is equal to the recessive trait, so for the widow's peak. So this male must be little w, and then the mother must have been big W, little w, because they weren't affected, and the father must also be big W, little w to end up with the little w trait. In the case of 7, then the genotype as well must be little w, and they are female. 6 is unaffected, so they are going to be big W, little w, or they could be big W. And then let's have a look. We actually know, so for 6, there are 2 possibilities. They could be big W, or big W, little w. Yeah, but because both children are affected, they must be heterozygous, so that they can combine with the little w of number 7. So when we have this little w with big W, little w, we can end up with the affected trait, where otherwise we would just not, if we had the big W, all of them would be heterozygous, big and little. So we couldn't get this recessive trait here. So we know that they must be, in order to have the affected children, it must be heterozygous for the recessive and dominant trait. So it's big W and little w in order to have the affected children. Then for 8, we can't actually tell. Because all 3 children are unaffected, it would imply that they might be big W. Okay, and this would be because if we big W in combination with little w, we would get big, little, big, little, big, little, big, little. This would provide the phenotype of all unaffected, which would be in line with this. But we can't be certain, because there is a chance each time that they may have an unaffected child, even if the individual was heterozygous. So this one we can't be certain of. They will either be a big W, little w, or 2 big W's though. Okay, let's move on. So that's interpreting a pedigree. We'll do some more practices in class, but this is using our reasoning to be able to work out what the parents must have been by having a look at the offspring and figuring out who's been affected and who hasn't. So this is our worked solution for what we just went through here. So 12 and 13 are brothers, but as we said, they're actually identical twins from the previous classification here. So have a look, see how you go with applying this solution with all my scribbled notes across the slide, and see if you can work it out. And I'll give you a few practices the next time we meet up in class.